In this video, we will take up the concept of work. Remember that we've already dealt with work early in the course. We said that the work done by a force upon an object. Well, let's choose an object to do work on. Let's say that we had a piston somewhere like this, and we applied some force upon that piston, F, and that we then moved the piston and have it has some displacement. So it was shifted some delta x. And we said that the change in work, that is the small amount of work we did moving it over this small displacement, was F delta x. Well, if that force is varying with time, and we start here at point A, then there's some F, and we did it over some delta x, and that represents this area of this rectangle. And to find the total work as we move it from some point A to some later point B, let's call this point A, and then later on somewhere we're going to eventually move it way out here, some appreciable distance to some new point B. The force may change during this time, as it does in this graph. And to find the total work, what we need to do is we need to find the area under this curve. That is, we need to sum up all the little delta W rectangles, or sum up these forces. Usually we put little subscripts where this goes from 1 to how many ever we have to add up. So, bottom line is, work done is the area under a force position graph. And that's earlier in the course. So nothing about that has changed just because we started studying thermodynamics. Furthermore, if the force is in the same direction as the displacement, which in this case displacement's in the positive x direction, if the force is positive, that is if we're going in this way, then you get positive area. If on the other hand you were going a displacement in the negative x direction, but the force is positive, then this work would be negative, and this would be negative area. So positive area work going from A to B, but we previously noted that it was negative work going from point B to A because the displacement vector is in the opposite direction of the force vector. What's changed now? Well, let's consider our piston that we're doing here. There's our piston, and we're going to push that piston over here, as we talked about, and we're going to push that some delta x. But instead of force, we want to think about it in terms of pressure. So inside this container, it's not a person pushing it, but a bunch of gas molecules banging along it. That is, there's some P. And to find the force, assuming that this has an area A, the force applied by the gas to the piston is the pressure by the gas times A, the area of the piston. Putting that into our formula for work, then the amount of work, delta W, is equal to the force times delta X, but we replace force with pressure times area, So it's P times A times delta X. And now I want to group the area times delta X. Now the area is right here. Delta X is this displacement. What that represents is a volume in this tube, which I will call delta V. So as this piston gets moved back, let's say that the gas was sealed off here, as that piston gets moved, the volume of the gas increases by this amount, delta X times A. So that's the formula for calculating a small change in work due to a pressure of a gas. That's volume, not velocity. So P delta V is delta W, and it's simply a restatement of the work that definition we had many chapters ago. Now, that means that I should be able to change this force diagram here, which is force delta X, into a P delta V. And in fact I can, and that's what's done. So the area under a pressure volume graph, plotting pressure in place of force and volume in place of displacement from point A, say, to some point B. If you are to find the area under this graph, that's the work by the gas upon the piston. So in gases, you can find the work the gas does by plotting the pressure of the gas versus a volume on a diagram. These pressure volume graphs, which are so useful for calculating work, are called PV diagrams. Remember, we've already seen that PV also has a place in terms of the internal energy through the ideal gas law for that system. So if we have a fixed N and we know P and V, then we'll know temperature because it's connected through the equation of state. If we have a fixed number of N's, it's only necessary to plot P and V in order to determine everything else about the property. So this point at A represents a particular state of the gas with specific properties: particle number, temperature, pressure, and volume. This point on the PV diagram is a different place. It may have the same particle number, but it has a different pressure, different volume potentially, and a different temperature. Each point along this path is a state, provided these changes are made slow enough so that the thing reaches some sort of thermal equilibrium. Now, we will take this in the next section and attempt to look at where does the energy come to do this work. You can't do work, that is, you can't transfer energy to the piston and increase its kinetic energy unless you're getting that energy from somewhere. Whether that's the internal energy of the gas or that's by energy you're obtaining from heat or some other means, you have to get energy from somewhere. And that will be the goal of the next video.